Hi everybody, welcome to video 7, 3.3, increasing, decreasing, and the first derivative test, part 2. So what we're going to do today, after we do a quick warm-up, is actually look at graphs to see the relationship between the derivative and the function itself. All right, so let's go ahead and begin though with this first little warm-up example here. So we are given that the line y equals negative 9x plus 4 is tangent to the curve f of x equals x cubed minus 6x squared at the point AB. We need to find AB. So when I'm told that, and I'm told that this is our tangent line, okay, remember the tangent line, its slope is the derivative of our function at a certain point, okay? So what we need to do first is we need to find what the derivative of f is, okay? So when we go through and find the derivative of f, we get 3x squared minus 12x for f prime. What we need though is we need f prime to equal negative 9. So we want to know what x value gives us a slope of negative 9, okay? So we set our derivative, f prime equal to negative 9, and we go through and we solve that, and we get two x values here. So what we need to do next though, once we have these x values, is we need to figure out the y values that correspond to those. So what we're going to do is we're going to take those two x values when x is 3, we're going to plug that back into our original function to figure out what the y value is, okay? And we're going to do the same thing when x is 1. We're going to plug it into f, and we're going to get our y value. So what we need to figure out is what is the equation of the line through those 2 points, okay? So we know the slope is negative 9. If we were to write this equation of the line in point slope form with the slope of negative 9, and we kind of clean it up to look like the original that was given to us, we don't get the same equation, okay? We're not getting y equals negative 9x plus 4, okay? But when we plug 1, negative 5, and we create, or we write the linear equation there with point slope form, clean it up, we see that it matches. So therefore, we can make our conclusion that it is that line is our tangent to the curve at the point when A, or our x value, equals 1, and when B, our y value, equals negative 5. Now we're going to look at graphs, okay? So the first set of examples goes along with sketching f prime given the graph of f. Okay, so I'm going to kind of walk you through this first one, and then I want you to try the second one on your own before you take a look. All right, so if we're taking a look here, this is our function f. What you should notice is f is monotonic decreasing and it's linear. Okay, so the key here is it's linear. That means f prime is going to be constant. But what you should also note is that since it's a line, notice what kind of slope it has. You should recognize it's a negative slope. Okay, so f prime is going to be negative. Now, you could take it a step further, and you could go ahead and figure out what the equation of that line is, and we can. So the equation of that line is f of x equals negative x plus 2. So if we were to take the derivative, we would get our derivative to be negative 1. So we could go ahead and sketch the graph. Our graph of f prime is going to be a constant, a horizontal line at y equals negative 1. Before I show you the next example, I want you to try to look at it and figure out what f prime might look like. Draw a sketch. So what I want you to pay close attention to is what is the behavior of f? When is it increasing? When is it decreasing? And what effect does that play on f prime? So pause the video now, take a look at example B, try to sketch f prime, and then come back. Okay, take a look. Did you get this for f prime? So what I did here was I looked at our graph of f, okay? And what I broke it down to, and I drew in these dashed lines just to help me visualize everything. So what I noticed is at this point, F is decreasing up until this where I draw my vertical line, okay? So I made note of that. F is decreasing. But then what happens to F? Then between these two vertical lines, F is now increasing, okay? And then I keep going and I say the same thing. F is decreasing here, and now we're back to increasing. So what does that mean? So if I break my graph up into these vertical lines, I can now talk about F prime. When F is decreasing, that tells me F prime is negative. And when F is increasing, we're positive. So you can see how the rest play out. So now how am I going to graph this? Well, what you should note is that F goes from negative to positive at this X value. So I need a point on my X-axis here. And I need a point on my X-axis here as well as here, okay? That is when F prime changes value, okay? Goes from negative to positive or positive to negative. So that's when F prime equals 0. So now I know, okay, F prime is negative, so I have to start when Y is negative down here, and I go through that point on my X-axis, and I continue drawing my curve for my possible sketch of F prime. Okay, our next example is the reverse. Now we are given the graph of F prime, and we have to sketch the graph of F. So we're working in reverse, okay? So I take a look and I say, okay, well, what do we know about F prime? Okay, one, I notice that F prime is constant. I also notice that F prime is positive. So since F prime is constant, I know F has to be linear. Since F prime is positive, I know F is increasing. I could also say that the slope is 2 because my graph of F prime is Y equals 2. Okay? So all I have to do is I'm going to just draw a line where I have a slope of positive 2. And there is our graph of F. And I should have labeled it. Okay? All right. So I want you to try this next example on your own. So look at part B. Again, look at the behavior or the value of F prime. Is it positive? Is it negative? Where does it change? Okay? And then see if you can actually graph F on your own. Then come back and check. Okay, so I noticed that F prime changes from positive to negative, or sorry, from negative to positive. At this point, X equals 2. So that's where I drew my vertical line, my little dashed line to help me out, okay? All right, so F prime is linear, so then we kind of have to think in reverse. That means I'm going to have F as a quadratic, okay? Then I made a note, F prime is negative in this section and positive in this section. So over on the left, I know F is going to be decreasing, and then on the right, F is going to go to increasing. So I just put a point somewhere along this vertical line, and I knew I had a quadratic, so I could go ahead and put my parabola in. Now, did my parabola have to be here? No, not necessarily, but this is just a rough sketch. Could we get more specific? Yes, we absolutely could, but we're not looking at the specifics right now. Go ahead and try example C on your own. Come back when you're done. Okay, so I noticed that F prime goes from negative to positive at this point right here when X equals 0, so I drew my dashed line in. I also noticed that F prime goes from positive to negative at X equals 2, so that's why I drew in my dashed line here. Okay, so then I label everything. So F prime goes from negative to positive to negative. So what's F doing? Well, if F prime is negative, F is decreasing. When F prime is positive, F is increasing. And again, negative means f is decreasing. So I just put some points randomly. Again, we're not going to worry about the specifics here. And I'm going to draw a function from left to right. I start by decreasing, and then at this point I switch to increasing, and then at this point again I switch to decreasing, and there is our function f. Okay, now again, this is just a rough sketch. It's not precise, and that's all we're looking for right now. Okay, this next example is really, we can use our calculator for a little bit of it, but it's really, in the grand scheme of things, we're just trying to prove that one function will always be greater than another function. Okay, so I filled this table out for you. All I did here was, okay, if we're given f of x is x, and g of x is sine of x, and we are on this interval, if we complete this table, all right, when x is 0.5, we get f of x to be these blue values, and when g of x is all of these x values, we get these green values here. So take a second to copy that table, pause the video if you need to, and then we're going to look at each section. Okay, so we're going to use our calculator to graph the functions and use the graph to make a conjecture. So if you graphed both of those, let f of x go into y1 and g of x into y2, you should be able to recognize that f will be greater than g. Okay, but now we need to prove that. So how can we prove that f is greater than g? Well, let's just go ahead and create a new function that we're going to call h. Okay, and we're going to let h be f minus g. Okay, and what we're going to do is we're going to prove that h prime is always greater than 0. Okay, and if we can do that, then we can prove that f is greater than g. All right, so if we let h be f minus g, and we plug in, we really get x minus sine of x. Okay, all right, so now all we have to do is just show that h prime is greater than 0. So we find the derivative of h, and we get this to be h prime, 1 minus cosine of x. All right, so we want to find when h prime equals 0. All right, so if we set h prime equal to 0, what do we get? Well, we should get 1 minus cosine of x equals 0. We get cosine of x equals 1. Well, what do we know about cosine of x? We know cosine of x will always be less than 1, right? Will always be less than 1. So we can go ahead and say, therefore, 1 minus cosine of x, which is h prime, will be greater than 0 on that interval from 0 to pi. Now notice it's this closed interval from 0 to pi, okay? Or sorry, open interval from 0 to pi. All right? So since that's the case, we can then conclude that f will always be greater than g on that interval. If you have questions from today's video, make sure you ask in class next time we see each other.